Assalamu alaikum. We learned that control systems are very important and they find many industrial applications. And to control something, we need to know its behavior. And the behavior of a system can be described by mathematical modeling. And in today's lecture, we shall talk about mathematical modeling of mechanical systems with rotational displacement. We have already revisited our understanding about mathematical modeling of electrical systems and mathematical modeling of electronic systems. For mechanical systems, there are two types of displacements: translational displacement and rotational displacements. In the last lecture, we talked about mathematical modeling of mechanical systems with translational displacement, and in today's lecture, we shall discuss mathematical modeling of mechanical systems with rotational displacement. Like mechanical systems with translational displacement, there are three basic components in mechanical systems with rotational displacements. These three basic components are rotational spring, rotational viscous damper, and inertia. You remember the strategy to model the mechanical systems with translational system was to write force balance equation, and for rotational displacement we write torque balance equations. That is, sum of the torques acting on a body in clockwise direction is equal to sum of the torques acting on that body in counterclockwise direction. Before we take some mechanical system and obtain its mathematical model, we briefly describe these three basic components. You may have seen a rotational spring that can have different shapes, and likewise viscous damper can have different shapes. The first element is the rotational spring. When we apply a torque on this spring, it produces an angular displacement theta of t. This torque and angular displacement are related by this equation. That is, the angular displacement is proportional to the applied torque. The proportionality constant K is the property of the spring and is called spring constant. The same equation can also be written like this one, where omega is the angular velocity, and we know that integral of angular velocity is the same as angular displacement. The second element is the viscous damper, and when we apply a torque, it produces angular velocity, and that is, angular velocity is proportional to the applied torque. The proportionality constant d is the property of this damper. This equation can also be rewritten like this one, d theta by dt is the angular velocity. Third basic element is inertia, and when torque is applied to an object, it produces angular acceleration. The angular acceleration is proportional to the applied torque. Proportionality constant is denoted by J. This equation is the same as this equation, only we have replaced d omega by dt by the second derivative of angular displacement. In the case of mechanical systems with translational displacement, we had introduced the concept of mechanical impedance. The same can be introduced for mechanical components with rotational displacement. The impedances of different components are written over here. The impedance of spring is K, the impedance of viscous damper is D into S, and for inertia it is Js squared. In the next slide, we briefly revise our understanding about the concept of mechanical impedance, and then we shall work out mechanical impedance for some basic component. Electrical impedance, you already remember, is given by the voltage divided by current, and if we analogously define impedance for mechanical component, that is a mechanical component for translational displacement, that should have been defined as force divided by velocity, because force is analogous to voltage and velocity is analogous to current. However, we had misdefined it, that is, since we are more interested in position, so we had defined mechanical impedance as force divided by displacement. And similar to this one, we define mechanical impedance for rotational displacement, and that is the torque divided by angular displacement. Consider, for example, the viscous damper, and its impedance, mechanical impedance, is torque divided by angular displacement. This relation relates torque with angular displacement. The same relation written in Laplace domain is given by T of s is equal to d multiplied by s into theta of s. Therefore, the ratio is T of s over theta of s is d multiplied by s, which is the mechanical impedance of a viscous damper with rotational displacement. In the same manner, you can derive expression for mechanical impedance of rotational spring and that for inertia, which were written on previous slide. Now we have we have studied the basic understanding of mechanical components that are involved in rotational displacement. We take an example to demonstrate the concept for mathematical modeling of mechanical systems with rotational displacement. The strategy to obtain mathematical model is the same as that for mechanical systems with translational displacement. That is, first of all, we identify the number of linearly independent displacements. Then we sketch free body diagram. Once we have free body diagrams, we can write the torque balance equations to obtain a mathematical model. So consider, for example, this mechanical system with this inertia J1 and another element with inertia J2. There are dampers D1 and D2, and there is a rotational spring K. We have applied a torque over here, and if we look this figure from the right, this torque is acting in clockwise direction. This end of the damper is fixed, and when we apply this torque in clockwise direction, it will produce an angular displacement, and let's name this angular displacement as theta 1 of t. Again, this element is a rigid element, that is, this end of this element has the same angular displacement as this end, so the angular displacement of this end and this end is the same, which is theta 1 of t. For the spring, this end has displacement theta 1 of t. This end can have different angular displacement, and let's name as theta 2 of t. Again, there is inertial element, and this end of this element and this end both have the same displacement theta 2 of t. This end of the damper is fixed. So there are two independent angular displacements in this diagram. Next step is to write the free body diagram, and you remember the procedure for obtaining free body diagrams. For example, if we wanted to obtain free body diagram corresponding to this displacement, the steps were: first, keep this object stationary and determine the torques which are being applied on this object, and in the second step, keep this object stationary and move it in the direction of theta 2 and determine the forces which are acting on this object. So this figure shows the torques which are applied on this object when this element is kept stationary. So here this theta 1 is this angular displacement, and t of s, now we are writing everything in Laplace domain. T of s is the externally applied torque which is in clockwise direction. So when this torque is applied in this clockwise direction, and this there is angular displacement theta 1 in clockwise direction, this damper will apply a force in counterclockwise direction. Not force, torque. Apply a torque in counterclockwise direction, and the magnitude of that torque will be proportional to angular velocity, that is d1 s theta 1 of s. This spring will also apply a torque which will oppose this direction, that is it is in counterclockwise direction. Magnitude of this torque is k theta 1 of s. This inertial element will also apply a torque, and that is always opposite to the direction of acceleration, and this is given by this expression j1 s square theta 1 of s, because the magnitude of the torque applied by inertia is proportional to acceleration, and s square theta 1 of s is the Laplace representation of second derivative of theta 1 of s. So this diagram is obtained by keeping this object stationary and determining all the torques which were acting on this object. Next, we keep this object stationary and move it in the direction of theta 2 and determine what torques are being applied on this object j1. So if this has angular displacement theta 2 and this is stationary, now spring will tend to, if this end is rotating in clockwise direction, this spring will tend to rotate this object in clockwise direction, that is spring will exert a torque on this object in clockwise direction, and the magnitude of the torque is proportional to the angular displacement, that is k into theta 2 of s, k into theta 2 of s, and in clockwise direction. The overall free body diagram for this object is obtained by summing up all the torques which are acting which are represented in these two diagrams. Therefore we have this free body diagram which includes all the torques shown on this figure and all the torques which are shown on this figure. Once we have this free body diagram, then writing a mathematical model, that writing an equation is very easy. Sum of the torques which are acting in clockwise direction is equal to sum of the torques which are acting in counterclockwise direction. So that is given by this equation. Here this torque was in clockwise direction, and when brought to the left hand side of this inequality, here it becomes a negative sign. In the previous slide we obtained a free body diagram for this displacement, and now we obtain free body diagram for this displacement theta 2. The steps are the same. We keep first we keep this object stationary, fixed, and move it in the direction of theta 2, determine all the torques which are acting over here. So when this object rotates in clockwise direction, this spring will resist this angular displacement, that is, it will exert a torque in opposite direction, and the magnitude of that torque will be proportional to the angular displacement. That is, this spring will exert a torque in counterclockwise direction, and its magnitude is k theta 2 of s. Similarly, this damper will also oppose this angular displacement, that is, it will apply a torque in counterclockwise direction, that is given by d2 as theta 2 of s. This inertial element will also oppose this angular displacement, and the magnitude of the torque that is applied by this inertial element is proportional to the angular acceleration, that is j2 s square theta 2 of s. This free body diagram is obtained by keeping this stationary and moving this in direction theta 2. Next, we move it in the direction theta 1 and keep it stationary, determine all the torques which are being applied on this object. So if this object is rotated in the direction of theta 1, that is in counterclockwise direction, in clockwise direction looking from the right, then this spring will tend to rotate this object in the same direction as theta 1, that is, it will exert a torque in clockwise direction on this object, and that is represented over here. Collecting the information in this diagram and in this diagram into a single diagram, we have this free body diagram which represents this angular displacement. And once we have this free body diagram, we can easily write the torque balance equation. Sum of the torques acting in clockwise direction is equal to sum of torques acting in counterclockwise direction. All these torques are in counterclockwise direction. This torque is in clockwise direction. When brought to other side of inequality, we have a negative sign over here. So this mechanical system with translational displacement is modeled by these two equations. If we carefully look at these two equations, what we observe is that theta 1 of s is being multiplied by sum of the impedances which are connected to displacement theta 1, and theta 2 is multiplied by negative sign and sum of the impedances which are common between theta 1 and theta 2. This impedance is connected to both displacement theta 1 and theta 2, so this impedance of the spring is common between the two displacements, that is over here. The right hand side is sum of the torques which are externally applied on this displacement, so T of t is applied to this displacement externally. In Laplace domain, it is T of s. The second equation is theta 2 of s multiplied by sum of impedances connected with this displacement theta 2. So this impedance j2 s square is connected with this displacement, d2 s is connected with this displacement theta 2, and k is connected with this displacement theta 2. So this term plus theta 1 of s multiplied by a negative sign and into the sum of impedances which are common between displacements theta 1 and theta 2. The right hand side is sum of externally applied torques to displacement theta 2. There is no external torque applied to this displacement, so right hand side is equal to 0. So similar to the situation which we discussed for mechanical system with translational displacement, we have a shortcut, that is theta 1 multiplied by sum of impedances connected to this motion theta 1 minus theta 2 multiplied by sum of impedances common between theta 1 and theta 2, equal to sum of the applied torques at displacement theta 1. Similarly, the second equations, remember that these equations are these shortcuts are valid only if the directions of angular displacements and torques are taken as shown in this figure. If that is not the case, we have to modify this shortcut. We have to somehow change the signs associated with these angular displacements. Furthermore, you can apply these shortcuts as long as you know the basic understanding of the concepts. And thirdly, in this figure there were two independent angular displacements, therefore we had two equations. If you have more number of independent displacements, then you will get more equations which can be extended from these two equations. Once we have these equations describing the mathematical model, we can also obtain the transfer function. Let's assume that we are interested in obtaining a transfer function between angular displacement theta 2 and the applied torque T of S. We can proceed in different ways. For example, we can apply the Cramer's rule. For that purpose, we can write these equations in matrix form as shown over here, and then apply the Cramer's rule, which is given by theta 2 of S is equal to determinant of this expression divided by delta. If we expand this determinant, so this term multiplied by 0 minus this term multiplied by T of S, which is written over here, this delta is determinant of this matrix given by this expression. And if we bring T of S to the left hand side, we have a transfer function which describes the mechanical system shown on the last slide. To practice the concepts, we have one more example, and we have a mechanical system where an external torque T of T is applied to this arrangement. We want to apply the shortcut method to obtain mathematical model. For that purpose, we first identify the linearly independent displacements. When we apply a torque to this object, it produces an angular displacement, and let's name this angular displacement as theta 1 of t. This end of the object has the same displacement as this end, so this end has also angular displacement theta 1. Now one end of spring has this angular displacement theta 1, the other end can have a different angular displacement. Likewise, for damper, one end has the same angular displacement as this object, the other end can have a different angular displacement, and let's name as theta 2 of t. This end of the spring, this end has this displacement, the other end is fixed, so it cannot move. Likewise, for this damper, this end is fixed and cannot move. So the mathematical model is easier to obtain. Theta 1 multiplied by sum of the impedances connected with theta 1. So impedance of this object, that is 1 multiplied by s square, is connected with this displacement theta 1. Impedance of this viscous damper is connected with this displacement theta 1. Impedance of this spring is connected with this displacement theta 1. So S, which is impedance of damper, impedance of the spring, minus theta 2 of S multiplied by impedances which are connected to both the displacement theta 1 and theta 2. This end of the spring is connected to theta 1, this end is connected to theta 2, so impedance of this spring is common between the two displacements. Likewise, this end of the damper is connected to theta 2, this end is connected to theta 1, so impedance of this damper is common between the two displacements, theta 2 of s multiplied by s plus 1. The right hand side is equal to sum of externally applied torques applied to displacement theta 1. So T of t is applied to this displacement. Similarly, for the second equation, theta 2 of s multiplied by the impedances which are connected to this displacement. So impedance of this damper, impedance of this damper, likewise impedance of this spring and impedance of this spring are all connected to this displacement theta 2. Theta 1 multiplied by a negative sign and sum of impedances which are common between theta 1 and theta 2. So that is s plus 1. There is no external torque applied to this displacement, so right hand side is equal to 0. Again, to obtain the transfer function between, for example, theta 2 and t of s, we can apply Cramer's rule, or we can proceed in a different way. For example, we can eliminate theta 1 from both the equations and then obtain a relation between theta 2 and t of s. So this is these are simple equations, so maybe the second method of elimination would be easier. From this equation, the second equation on this slide, we have theta 1 of s is given by theta 2 of s multiplied by this term, that is bringing this term to the right hand side and dividing this, we get this expression, and taking 2 common from the numerator, this numerator term is cancelled with denominator, so theta 1 of s is equal to 2 theta 2 of s. Now we substitute theta 1 equal to 2 theta 2 into the first equation on this slide to get this equation, which can be simplified to obtain this expression, that is 2s square plus s plus 1 multiplied by theta 2 of s is equal to t of s, which can be rewritten into this form, and this is a transfer function for this mechanical system with theta 2 as output and t of t as input. In the next lecture, we shall talk about mathematical modeling of mechanical systems with gears. Gears are very common in mechanical systems with rotational systems, and that will be discussed in the next lecture, inshallah.